I'm going to start over because I forgot to begin recording. So today's class, we're going to take a closer look at the metal ligand bond. And so far, you guys should be able to look at a complex ion and say that identify complex ions. You should be able to identify ligands and classify them as anionic or neutral ligands. You should be able to calculate the oxidation state of the metal ion center. You should be able to identify different geometries and coordination on both. And so today, what we want to do for today and our last class for next week, we're going to look a little bit closer at the metal ligand bond to see if we can kind of understand more about what this interaction is. Keep in mind this is a first year class, and so we're going to go off slow. And if for those of you who go off, move on further into chemistry, you learn just exactly how complicated and how complex the metal ligand interaction is. All right, so let's continue. So from the beginning of class, we've basically envisioned the metal ligands as the metal ligand interaction as Lewis acid and Lewis base interaction, where my metal has empty orbitals, so it's a Lewis acid, and it can accept 2 electrons from a Lewis base to now form a coordinate bond. All right, and we're looking at it in this way. Essentially, all the metal ligand bonds are covalent bonds, or specifically coordinate covalent bonds, where both electrons again are coming from the Lewis space. All right. So for our class and for the sake of this class, we are only going to view the metal ligand interaction as a sigma type interaction. You can have pi bonding, but it's outside the scope of this course. We're going to focus mainly on sigma type interactions. It's going to be head-to-head interaction to now give us our coordinate bond. If we start to dig in further into the bonding, some things that should strike out to us. All right, so here is I'm showing you this cobalt 3 D6 metal, right? Coordination number equals 6, and it's an octahedral complex. And so if we were to go and calculate the d electron count, we will see that it is D6. And if we were to add the 6 electrons, we can draw them out in this fashion, right? So here it is, a D6 complex with 6 electrons in my d orbitals. So for the first question, how many electrons do d orbitals hold? So I have 6 electrons here. How many electrons can I populate into my d orbital? Casella?
10, Miss.
10, right? And that's because I have 5 d orbitals, and each one of these orbitals can hold 2 electrons, so I can hold a total of 10 electrons, right? So I can hold 10 electrons. Next question is, how many electrons will each ammonia ligand donate to cobalt? All right, if I look at, pardon? Someone says 12.
You donate 2 electrons.
So each one would donate 2 electrons, and there are 6 of them, so I'm expecting there to be 12 electrons to donate. And if we look at bonding just from this very simple, simplified picture, we realize we have a problem here, right? Because we only have space to fit 4 more electrons in the 3d orbitals. So for those of you who are wondering, when we form these complexes, where do the electrons go? It's a natural question to ask. And they don't, I can tell you right now, they do not go into occupied d orbitals. Yes, Casella?
They're going to the 4s orbital.
All right, we're on the ball today. So where do they go, right? And where they go, they actually go on all the orbitals in the on the metal ion. So they're going to empty hybrid orbitals, right? So the d orbitals are in essence here, not partaking in the bonding. Right? They're not partaking in bonding. So therefore, where the electrons go are in hybrid orbitals. Just like when you guys did methane in organic chemistry and you saw hybridization of an S and 3p orbitals give you sp3 orbitals, what happens in this case is that a 4s, 3p's, and 2d orbitals can hybridize now to give me 6 new orbitals, sp3d2 orbitals. And it's into these orbitals that those 12 electrons from ammonia are going to occupy, right? So my ligands therefore are now donating into the 4s, the 4p, and 2 of the 4d orbitals to form that bond. So basically my 3d orbitals are essentially non-bonding and are partaking in bonding. Right? So here it is, I'm showing these sp3d orbital, and each one of the ammonia ligands is going to be donating into my cobalt. Right? We can carry out the same exercise if we were to look at a tetrahedral cobalt complex. So if I were to look at COCl4 2 minus, again, this is going to be D7, but my ligands are now going to occupy sp3 habitals. The 4s and the 4p are going to hybridize to form 4 sp3 habitals, and that is where my metal ligand bonding will take place. So get that? You see that?
No, miss, I don't get that.
All right, Justin, you have a question?
Yeah, so from here, we're saying that the 3D electrons aren't really partaking in the bonding,
Right. So 3D
but
orbitals, the 3D electrons aren't partaking in the bonding.
but at the same time, they're to account for some chemical properties.
Yes, they're going to be higher in
Uh,
energy. So therefore, when you actually oxidize the metals, don't stay with me. When you actually oxidize your metals, or you're actually moving the d orbitals, or the d orbitals. One of the reasons for this, if you guys go back to when you started molecular orbital theory, or the molecular orbital theory, something you should have touched on was that your orbitals have to be symmetrical, right? So if you think about which orbitals your electrons are on ammonia, right? On the shape of those orbitals and your SPs, then you have to think about, and that again is outside the scope of this course. Marcel is in the chat. Hi, Marcel. Welcome. All right, Daniel, question.
Okay.
Hi.
So the reason why they occupy the 4s and 4p and 4d orbitals because they're vacant, right? So
Yes, they're vacant.
they will be lower in energy than the 3d orbitals.
Yes,
So that's why they
they're
will
going to
fill
be lower.
first.
Right, so those will fill first, and the 3D orbitals are actually going to be higher in the complex, right? So those are where those electrons are going.
Okay. Thank you.
All right, yeah. All right, any other questions?
so Miss
Yeah, who is this?
Justin,
Hi, Justin.
um, so it would occupy the it would hybridize the lower electron
It's
orbitals.
going to hybridize the 4s, p, and d are going to hybridize, and they're going to become lower in energy than the 3D because they're going to start forming bonds with your ligands. So
Uh,
again, I don't want you guys to overcomplicate this, but I want you guys to understand if you're looking at this and you're confused and you're like, if ammonia is bonding to a metal center, it's donating to each ammonia is donating 2 electrons of an oxyhedral complex. Where do those 12 electrons go? Just know that they're not going into the 3D orbitals. They're going into other vacant orbitals, which would be the 4s, the 4p, and the 4d once they hybridize. So don't give us new orbitals. And that's
okay,
according to valence bond theory.
okay, okay.
Right?
Thank you.
Okay, no problem. Okay. So yes, Rajan, it's kind of like carbon hybridization, where for methane, when you have 4 identical CH bonds, we now use we said that an S and 3p's hybridize together to now give us 4 new sp3 orbitals in order for bonding to take place. And keep in mind that this is valence bond theory, right? Right. So none of the donated electrons go into the d orbital. The d orbitals are non-bonding in this sense. All right. So we're going to skip that. And again, if you start going more complicated, if you're interested, you will realize that this thing gets more complicated. But that's where our ligands go. They're going vacant, hybrid orbitals on our metal ions. So give me a second. Right? All right. So let's continue. All right. So this does not fully explain the metal ligand bond. So for instance, if I were to look at cobalt CN63 minus, we find that it's diamagnetic. What? Actually, I'm going to skip this slide over. All right. So one thing about transition metal complexes is that they are colorful, but they also show magnetic properties. So if I want to know if a complex actually displays magnetic properties, I can use what's called a GUI balance. I'm showing a GUI balance here. And it's just what it is that you have a powerful magnet, and you have about a weight and a balance. And when the magnet's off, it's balanced. Your weight and their thing is balanced. It's equally balanced. If your complex is paramagnetic, when you turn the magnetic poles on, it's going to now attract your compound, and it's going to cause it to, it gets attracted and it goes down, right? If you now have a diamagnetic complex, so that means diamagnetic means that all your electrons are paired, and you turn on your balance, now it's going to cause your complex is going to repel the magnetic field. So if I have a paramagnetic unpaired electron, it gets attracted magnetic field. And if I were to have diamagnetic, meaning that I have paired electrons, it gets repelled by the magnetic field. So let's do an experiment. So here I'm showing you two iron complexes. I'm showing you a hexaquo iron complex and a hexacyanoferric complex. I want you guys to quickly calculate the oxidation state and the electron count of iron in both of these coordination complexes. And furthermore, based off what we said before with the how the amount of electron d orbitals, tell me how would you expect each of these to behave in a GUI balance? Okay, I'm seeing one answer. Rajan says that they're going to be both +2. He says +2. Mia says +2. That +2 for both. Remember that there's 4 potassium on the outside. All right, so far we're seeing that that both ions here are +2. And if they're +2, what is my d electron count?
6.
I heard a 6, so they're both. So therefore, they're both going to be d6. All right, good. We're good with that? Okay. So how would you expect these to behave if I were to throw, based off looking at the bonding theory we're looking at before, which is valence bond theory, how would we expect these to behave in a GUI balance? Right? So therefore I have D6.
Paramagnetic.
So you'd expect both of them. All right. So how would you, all right. Would we expect the hexaqua species to be attractive? All right. I'm seeing people saying they will be attracted. Attract to the magnet, attraction. All right, cool. So based off what I just told you and based off the previous bonding model we're looking at, we would expect both of these species behave the same when we put them into a Dewey balance because they're both iron 2 plus, they both have 6 electrons, so therefore we're expecting to have 4 ampere electrons. If we put that in, it's going to be paramagnetic, right? So based off previous information, we'd expect them to be paramagnetic. And those of you who have been with me long enough know that that question was just a setup, right? It's going to get way more complicated than that. So we would expect, so both of E2 plus, and based on the valence bond model, we'd expect them to be paramagnetic. But as chemists, we can look at them and we can actually go into the lab now and actually do the experiment and see what we find out. So we'll do the experiment, and when we place our hexaco species in to the GUI balance, it gets drawn in, which means attracted to the magnet, and we say that it's paramagnetic. If we take now and look at our cyano complex, we realize that's repelled by the magnet, so therefore it's going to be diamagnetic. So clearly there's something else happening here on the electronic level that it goes beyond just what valence bond theory can tell us, right? So this experiment is telling us that the hexaqual is going to be paramagnetic and the cyano is going to be diamagnetic. And I see that somebody in the chat has already given away the ending, but we'll get there. All right. Do I have you guys so far? Right? So it's telling us that the complex itself and the iron, remember we're looking at the iron center, that the iron center in the hexaco is going to have unpaired electrons, and the iron center in the hexacyano complex is going to have paired electrons, right? And so when we measure the overall complex is going to be paramagnetic and diamagnetic, but the magnetism is coming from the metal itself, right? We don't really have water that's magnetized. All right, so let's move on. So in order to fully understand what's going on here, we have to now look at another theory of bonding. So what we were looking at before was called the localized electron model or valence bond theory. And we can use it to talk about geometry, so we can use to rationalize the formation of octahedral or tetrahedral complexes. However, that's as far as it goes. It doesn't really help us to explain why one iron species may be magnetic and the other species is non-magnetic. It also doesn't fully account for the color transition metals, right? So therefore, in order for us to have a better understanding of these complexes and what's going on with them in terms of bonding and the electronic level, we have to adopt a new theory. And so what we're going to look at in this class is that we're going to now start to investigate crystal field theory. So we're going to take our time and go through crystal field theory. It's a big part of the course, and I want you guys to make sure that you guys get it. And I'm really happy that Marcel is here so that he can actually help to explain to answer your questions as we go along. All right, so crystal field theory. What is it? So crystal field theory is an electrostatic approach to bonding. And so from we talk about electrostatic approach, you guys should be going back to like ionic bond, negative and positive interaction, right? So it's going to be electrostatic forces. And what it considers is how the interaction between the ligand point charges and metal d orbitals affect the energies of the d orbital. So that's crystal field theory, an electrostatic approach to bonding that's going to take place between the metal d orbitals and the ligands themselves. All right. So before we start this, we have to go back and refresh ourselves about the d. If you don't remember, the position of the orbital and this whole thing is going to be lost. So as I said previously, there are 5 d orbitals, right? And they all have 5 different names: d6 squared, d squared minus y squared, and so forth. And the name of the orbitals tells us about the orientation of the orbital in space if we were to have a Cartesian axis. So we're going to go. So I want you guys to look, and they're empty right now. And now to put, we're going to now draw envelopes for Miss, we aren't hearing you properly.
Um, Good afternoon, everyone. I'm indicating to Dr. Simpson now that she's not here
Okay.
and you guys are not here. Oh,
Can you hear me
okay.
now? Hello?
I can hear you.
All right.
Yes, I can.
All right, cool.
I-
All right. So what happens when you have two devices in the house? All right. Where did I leave you guys? Who's drawing on my screen, or is that me? Okay. All right.
Talk about the arbiter.
Or the d orbitals. All right. So in order for crystal field theory to make sense, you have to go back to the d orbitals and remember how they're oriented in space, and that's going to affect it's going to affect the energy level of the orbitals when we place them in different crystal fields. All right, so the first one is dz squared, and that's probably one of the easiest one. Squared orbital is probably one of the easiest one to figure out. Right? Why is okay, guys? I'm having some technical difficulties. My presentation is, for lack of a better word, bugging out. All right. So for dz squared, this orbital is going to be lying directly in the plane of the z orbital, right? And it's going to have what we normally call, when I was in grad school, we called a donut, a little donut, a little contribution in the xy orbital. So that's my dz squared. So dx squared minus y squared, if we were to draw that, what orbitals, what axis is my dx squared minus y squared? Where does that lie on? All right, xy plane. Yes, Justin. So who's drawing on my slide? All right, someone's making an effort. Okay. So it's going to be the x and y plane. So let's draw that a little nicer. All right. So we're going to draw it a bit nicer so that it doesn't look like that. So for the dz squared, for the dx squared minus y squared, it's going to be directly on the x-axis. Right? And how about the other ones? Guys, I'm going to close the presentation and come back out because my Blackboard is just not working properly right now. So I'm going to close everything down. I'll log back in and we'll start over again. I apologize for this. I just don't know what's going on right now with my screen and everything else. So excuse me while I pop out and then come back in. All right, sorry about that. Let's just continue. All right, so I said before that the dz squared is going to be on the orbital itself, directly on the z, with some contribution in the x and y. The dx squared minus y squared is going to be directly on the x-axis, x and y axis. And the dxy, dyz, and dxz, as your name suggests, is going to be in between the orbitals. So for the xy, the lobes are going to be between the x and the y. So here is x, here is y. So it's going to be between those orbitals. So one's going to be here, one here, one here, and one there. My dyz, it's going to be between the y and the z orbitals. So it's going to be between these two orbitals. So I'm gonna have one lobe here, one lobe coming this way, one lobe go that way, and one lobe go that way. And then finally, my dxz is going to be between the x and the z. So I'll have one here, one here, one coming here, and then one going out behind there. All right. So I have 5d orbitals, and they're going to be oriented differently in space depending on the data letter that they're assigned to. All right, so for crystal field theory for crystal field theory, and I'm showing you them here, so just so you can see them a little bit nicer than my drawing. We're going to say all 5 of the d orbitals, 1, 2, 3, 4, 5, we're going to represent them by 5 lines, 1, 2, 3, 4, and 5, right? And they're going to be degenerate. So if I have an isolated metal ions, it's by itself, all somewhere, it means that all my metal, it means that all my metals are going to have the same energy, they're going to be degenerate, right? We're now going for our ligands. We're going to call our ligands point charges. Therefore, each of my ligands, I won't see them as ammonia, chloride, or oxalate. I'll just see them as a negative charge for crystal field theory, right? So the orbitals, we're going to represent them by 5 lines. And my ligands, we're going to represent it by a charge. They're going to just be negative charges. Keep in mind that orbitals are places where you're going to have electrons. So therefore, they're going to be negatively charged. My ligands are going to be negative point charges. Therefore, if I put 2 negative things together, I'm expecting them to do what? To repel. All right. So hold on one. So all right, so let's go. So if we have my isolated d orbitals, they are degenerate. And the question now becomes, what happens to the energy level of my d orbitals if they're placed in a different type of negative charge? So the first one we're going to investigate is what happens if we put the d orbitals into a sphere of negative charge. What will happen to the relative energy? And the second one is what will happen to my d orbitals if I place it into a field of negative charge that basically had the shape of an octahedral. So think about it. So what do you think is going to happen? Or have I lost everyone with my going in and out?
Yes, miss.
You guys are lost?
Miss.
All right. So I'm saying is that we have 5 d orbitals, 5 isolated d orbitals, and we're representing them by the 5 dashed lines that you see here. All right. So when they're isolated, they're by themselves in a vacuum. There's nothing else around. They're all degenerate. They have equal energy. 1, 2, 3, 4, 5. They're all on the same energy level. So for crystal field theory, it's going to say that our ligands are going to be point charges, right? So therefore, it's going to be a negative point charge. And keep in mind that each one of my d orbitals is going to hold electrons in there. So therefore, if there's electrons in there, they're going to be negatively charged. So if I were to take now my d orbitals, and here's their energy, they have some ground state energy. And if I were to put them into a spherical charge, which means the charge around them would be the same, what do you think is going to happen to overall energy of all 5d orbitals?
Won't be degenerate anymore. Some of them gonna increase due to repulsion. Some of them will be more repulsion than others.
All right, but remember this time it's a spherical, right? So if it's spherical, they'll repel, which means that, but they're going to repel equally, because if in a sphere, you're all feeling the same amount of energy. So if I were to pick this, all of my orbitals would then rise in energy in the presence of a spherical negative energy. So they're all now surrounded by negative energy. They will all rise together to now become higher in energy, right? If they're placed in a spherical field. So whenever they are in contact with a negative point charge, they're going to increase in energy. So for a spherical field, it says that the negative charge is going to be equal for all my d orbitals. They'll rise in unison. So what happens now if I were to place this in an octahedral field? So what I'm showing you here are the 5d orbitals placed in octahedrons. I know for those of you who have done this before, I've read ahead, it's going to split. But how is it going to split, right? So for each one of my octahedrons, I can think of my ligands being, again, right, 6 ligands, and they're going to be located there. So which orbitals do you expect to get higher in energy or lower in energy based on if I now have a negative point charge, a ligand now sitting next to a dz squared, the dx squared minus y squared, the dxy, the dz, and the dxz, it says. So if I look at the orbitals in the octahedron, I will see that for my dz squared and my dx squared minus y squared, they line directly in line with my point charge for my ligand. So because of this, they're going to actually feel greater repulsion. They're going to feel great repulsion, right? So these two ligands are going to now get higher energy because now they're in direct contact with my with the negative point charge. However, if I now look at the dxy, the dyz, and the dxz, I see that they're not in direct contact. They're actually in between where my ligands would be. So here, this loop here, the dxy, is actually in between where my lobes would be, and as such, you can see here for the dyz, right? They're not in direct contact. And as a result, they're going to now become lower in energy. So now we're going to have the dxy, the dyz, the dxz, and they're going to be low in energy. So when I put my ICD orbitals into an octahedral field, which means octahedral point charges, negative charges around it, my dz squared and my dx squared minus y squared, which are in direct contact with these point charges, are going to have greatest repulsion, and they're going to increase in energy. And my other 3d orbitals, which are now lying in between these charges, are not going to be repelled and are going to become lower in energy. And this is what we call an octahedral field or an octahedral splitting diagram. So now my d orbitals become split when placed in an octahedral field. this is what it looks like. So in the first case, we talked about d orbitals, right, by themselves and the relative energy, if they're isolated, they're low in energy. If we were to put a spherical charge around them, right, the d orbitals will increase. And then if we were now to put an octahedral field around them, they will split into two sets, where now my d squared minus y squared becomes my e, we call it the EG set collectively for these two, and the dz squared, and then my other three become the T2G set, right? And this is my octahedral splitting diagram, which means now my d orbitals are now split into two parts in the octahedral. Things to take note of on this diagram, we have the gap between the two EG and the the T2G set is called delta octahedral, and this is a crystal field splitting energy, right? And we're going to talk some more about the magnitude, about how big this split is, because it's going to have consequences for color and magnetism, right? And we'll refer to it as delta O, or delta oct, or delta octahedral, and that's my splitting constant. All right, we're going to pause here. We're going into tetrahedral, and let's ask questions, and we'll take it from there. All right, so I saw that Justin had a hand up. Do you still have a hand up, Justin?
No, I was gonna ask if the energy level of the other three orbitals would be still higher than the initial if it wasn't in any field. But then I saw this.
Right, okay. Yes, everything's going to rise up in its spherical field, and then it's going to go lower than the spherical field energy, but higher than the isolated, because there is still some repulsion there.
Okay, thank you.
All right, questions. Again, this is the topic I hate teaching. Well, not hate. I like teaching. I think it's a fun part of chemistry, but it takes a while to actually get it. Daniel.
Yes, ma'am. The point charge, right, of the
Right.
which is the negative charge of the ligand, right?
All right, so the ligand doesn't have to have a negative charge for it to be, it's just all ligands in crystal field theory are seen as point charges.
Oh,
All right.
So since the point charge is between the d orbitals, right? For the ones that are lower in energy. If they're between, it would be lower in energy. That's why you would have dxy, the dzy, and the dz, and the other dxy one. That's why they will be lower in energy, because they're not in direct contact with the point charge, right?
Right, they're not in direct contact, so they're going to be lower than energy in the dx squared minus the dz squared. There's more to it in terms of the crystal field splitting, and if you guys read Chemistry 3, they'll talk about stabilization energy. We're not going to go into that for this course. What I want you guys to understand is that the d orbitals are split, and that there's two sets in octahedral geometry, where the top set is the EG, and the bottom set is the T2G set. All right.
So does it occur at the same time for this splitting to take place?
Yes, splitting is when, so once you're going to have an octahedral complex, the d orbitals are going to be split in this manner.
Okay, all right, thank you.
All right. All right, who else? Any other questions? All right. All right, so Lisa Marie.
Hi, Miss. I wanted to know why the d orbitals that are low in energy, or that become low in energy after the octahedral thing, why are they lower than initially, like how they were, instead of just lower than the ones that are directly in contact with the negative point charges?
All right, so if we can imagine that the ligands, when the ligands are out away and there's no geometry and it's equal distributed, then all the d orbitals are going to rise in energy, right? As shown in the second platform. The energy of the 5D orbitals increases when they're placed in a spherical negative charge. As the charges now start to come into an octahedral geometry, what's going to happen, you can imagine happening simultaneously, is that it's going to cause my EG set, which is my DZ squared, and my DX squared minus Y squared to become higher in energy. When these become higher in energy, my DXY, DYZ, and the other three, right, they become lower energy because of stabilization that comes along with splitting it. And this happens simultaneously, where two is high and the three go low. All right, yes, Daniel. Last question, and we'll try to. All right.
So
remember,
so the,
yes,
no, continue.
No, ask a question.
Oh, so when that happens, that would cause them to gain color.
So the color now comes from, because you have the splitting, the color is going to come from actually electrons going from the T2G set to the EG set, right? And the energy that promotes the electron from the lower set to the higher set comes from the visible spectrum. And that's why they're colored. And we'll talk about this more next week, or you guys can read ahead in the text. All right.
Stevenson, there in ChemStock last year, remember for research here, we did the whole transition metal cocktails. You could probably do that with them next week to show them the different colors that they can
Yeah,
give.
that was the plan for this week, but next week for sure we're going to make some transition metal cocktails that we will not be drinking. All right.
Okay.
So here it is, and we're going to summarize all we just talked about. So in the octahedral field, the dz squared and the dx squared minus y squared orbitals point directly along the three axes towards negative charge and will be higher than the other orbitals. These become higher in energy. The dxy, the yz, and xz point between the axes and will be less influenced by the negative charge. And as we see, these are lower in energy relative to the EG set. This leads to the splitting of the 2D orbitals into two sets, the EG and the T2G orbitals. And so when you guys talk about your electron count now, we can be more specific by saying how many electrons are in the T2G set and how many in the EG set, rather than just saying D6 or D7. We can be more descriptive. All right. So the octahedron is probably the easiest one to see. And we're only responsible for two splitting diagrams. That's octahedral, tetrahedral, and square planar. Tetrahedral is a little bit funkier to see just because you have to imagine being in a cube and imagine tetrahedron being in that cube. All right, so we're going to take our time and we're going to work through it. And for those of you who fancy 3D dimensional, this is very, very hard for you. Just know what the splitting diagrams look like and you'll be fine. All right, let's not lose any sleep over it. Although I'd love if you guys actually took the time to see why these geometries, why the orbitals are split the way they are. All right, so for octahedral, now we're going to look at a cube, right? So here is my octahedron, right? And if I were to put it into a cube, my ligands now will be here on the vertices of my cube. Note now that if I look at where my X and my Y and my Z axes are, I now begin to see that there's no ligands in the Z axis and there's no ligands in the Y, directly in Y and X axis, and my ligands actually lie in between those two different, right? It lies in between the X and the Y, but not directly in between, right? So if we were to do the same exercise we did before for octahedral and apply it to a tetrahedral field, how would we expect it to be different? Right? Let's start off with the two easy ones. Here are some little cubes with the orbitals in there, and I just want to highlight for you guys that the vertices are here, 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 and here. So probably the easiest one to see is a dz square, right? So here's my isolated ion again, would you expect the dz squared now to be higher or lower in energy? I have one person saying lower. All right, lower, right? Because now there's no ligands there, so therefore it's not going to have that level. All right, so we're going to expect our dz squared to be lower. How about our dx squared minus y squared? Is it going to be higher or lower in energy? All right, it's going to be lower energy also. Because again, it's directly on the plane and none of the ligands are there. And my dxy, dyz, and my dxc, I can take them as a thing. Are they going to be higher or lower relative to my dx squared minus y squared and my dz squared? All right, we have higher. So now, if I were to draw the splitting diagram for tetrahedral, here's my acid ligand, right? I'm now going to have 3 up top and 2 below. So my dz squared and my dx squared minus squared, and then dx, y, dyz, and dxc will be higher in energy, right? Because now they're not in direct path of, and I still will have delta O will still be here. So I still have a split. I still have a splitting
Could you please repeat that?
here. So again, we're doing the same thing as before, but unlike an octahedral case where we could see that the ligands were directly in the z plane, the x and the y plane. So for any orbitals directly in the x, y, and z plane octahedral, we're going to feel the most repulsion and higher in energy. In the tetrahedral case, my dz squared and my dx squared minus y squared, which are now going to be which are not in the path of any ligands, right? There's no ligands in those on that in the space that they occupy. So therefore, they're not going to be as repelled. They're going to be lower in energy. My dx squared, sorry, my dxy, dyz, and dxz. So if I look at where the ligand is, I see that they're not directly in line with those orbitals either, but they're close enough, and so therefore they'll cause them to be repelled more than the other two, and so therefore they'll become higher in energy just because they're closer to the point charge. They'll be higher in energy. So because none of my ligands are in direct contact, the splitting energy here is actually lower. We can call this delta tet for tetrahedral, but it's about half the magnitude of delta O. So it's going to be smaller than delta octahedral. Okay. So if I want to look at it and compare the two, so here's my tetrahedral, and my tetrahedral is inverted compared to the octahedral splitting diagram. So whereas in octahedral, my dx squared minus y squared and dz squared are higher in energy. In the octahedral, those are actually lower in energy. Delta tetrahedral is smaller than delta octahedral, and this is because none of the ligands come into direct contact with the d orbitals. So therefore, even the dxy, yz, and xz that are repelled, they're repelled much less so than the dx squared minus y squared and dz squared were repelled in the octahedral sense. Because of this, tetrahedral complexes, because it's always small, tend to be more paramagnetic high spin complexes than their octahedral counterpart. And when we talk about the ligands, the orbital set, we have the E and the T2 set, and we don't use G when we talk about tetrahedral because of the symmetry of the orbitals. So that's what tetrahedral looks like. The last one we want to look at is square planar, and it can be a little bit, so for square planar, what we're going to do is we're going to start off with octahedral and then see how the octahedral spin diagram will change if we were now to go from octahedral to a square planar complex. So if we look at this square plane octahedral complex here, there are 6 ligands. Square planar has 4, and the difference between the two is that if we were to take off these 2 axial ligands on my octahedral complex, I will get a square planar complex. So let's see if you guys are really getting this, for those of you who think you're getting this, and let's see who's kind of getting it. So if I were to remove these 2 ligands, so there's no longer ligands in the z-axis, right? And now my ligands are now going to be in the xy plane. What's going to be my highest orbital in my square planar complex?
Squared.
All right, that was fast. X squared minus y squared, because again, x squared minus y squared is going to be, my ligands are going to be directly on the xy plane, so it's going to be a lot higher. All right, so I love it.
Dr. Stevenson. But what if the ligand okay, what if the compound turn in a way where the ligands fall between the what is it? The xy plane instead of the x squared minus d squared? Because if you turn it, it kinda wouldn't it fall between instead of on top of the axis?
Oh, this is, the two things aren't oriented the same, but we can say that the dx squared minus y squared is going to be on the xy axis, right? And then if I were to put a square planar complex, it's also going to be in the xy plane.
Oh, okay.
Does that sort it out, or did I not answer your question? Okay. So if my dx squared minus y squared is going to be higher in energy, what will be the second highest one? dxy, right? So anything that's going to be in the x and the y position is going to have higher, is going to be higher in energy, right? So it's going to be my dxy. And then, so this is going to be higher in energy. It's going to go up, right? And so will my dxy. Now, because I've removed my ligands from, I've removed my my Z ligands, right? Anything with Z contribution. Therefore, anything with a Z is going to be lower in energy. So one thing that's tricky for you, and I'll just give it to you, the next one is actually going to be the DZ squared orbital. It still has some contribution in the X orbital because of that little lifesaver it has around it. And my last two is going to be the DXZ and the DYZ. They're going to be lower in energy, right? So that's the splitting diagram for a square planar complex. And you only have square planar when you have very strongly bound ligands. And then this whole thing here, the gap between the dxy and dx squared minus yz squared is actually equal to delta O, right? So that's my square planar splitting diagram. Okay. So I'm showing it to you here again. So removal of the ligands in the z-axis stabilizes the dz squared orbital, so it becomes lower in energy, and also lowers the dyz and the dxz, so those become lower in energy relative to the octahedral field. Things to note, for square planar complexes, we're only going to sit down for Da complexes, so D2, so nickel 2, palladium 2, platinum 2, and sometimes I throw out a copper 3 in there. The splitting again between xy and x squared minus y squared is delta O, so it's a pretty big splitting gap between those two orbitals. And what we'll go on to find out is that square planar complexes are only for strong field or for like metal ligands that have formed very strong bonds. And when we go to fill in electrons, so there's 8 electrons here, we'll find out that they're actually diamagnetic because all my electrons are paired up. And we'll see this again when we talk about magnetism, about magnetic moments and magnetism. So here are my three splitting diagrams. I have octahedral, tetrahedral, and square planar. And I'm showing you them relative to the free ion, right, and the magnitude of delta octahedral for each one of these, right? So you guys can just compare all three of them to see how they change relative. So again, this all takes time. So just take the time to just like read through the text, and then look at it and go back over the lecture notes and the lecture and see if it's everything clarifies. All right, so I have to log on, log off for during this lecture, so I'm gonna just beg you for 5 more minutes so we can finish up. Yes, Justin.
Um, I had a question. Is I forgot my question. I'll get back to you later.
All right, Justin. Okay, so we're going to take a little bit to talk about delta octahedral, which is actually very important. This is the crystal field splitting energy, and it's a gap between two sets of orbitals. When we did octahedral, we saw it was between the T2G set and the EG set. For tetrahedral, it was between the E set and the T2 set, and for square planar, it was between the dx squared minus y squared and the dxy. Right? So the magnitude of delta octahedral, we can determine this spectroscopically. So we can actually we can take a transition metal complex and we can put it in solvent and we can do a UV-vis spectrum on it, and we can actually measure delta octahedral to see how big that gap is, right? And how big this gap is dependent on two things, the metal ion and the ligand bonded to the metal ion. So, all right. So if we have a weak field complex, it means that delta is small. So if you look at here against octahedral complex, right, we know it's octahedral because there's an EG set and a T2G set, and here delta is small, so therefore there's a small gap between the two. If I have a strong field or a low spin complex, then delta is large, right, and I have a large gap between the two. And this is going to influence how I pair my electrons, and also the magnetism of my complexes. So factors affecting the magnitude of delta octahedral. So now if I were to look at some cobalt complexes, so here we have chromium hexaquo and another chromium hexaquo species, and one is the +3 oxidation state and one was the +2 oxidation state. If I were to look at how big delta O is, and the bigger the number is, the bigger that gap is, right? I see that for higher oxidation states, the chromium 3+, delta octahedral is actually bigger, right, in the 3+ state than in the +2. If I do the same exercise with iron hexaqua species, iron 3 and iron 2, I see that for iron 3, delta octahedral, the split is bigger for iron 3 than it is for iron 2. And we can get from this is that delta octahedral increases with increasing oxidation state. So therefore, if I had an iron 2 complex and I were to oxidize it, and if I were to measure delta O, it would actually increase upon oxidation. And this is because now when I have a higher oxidation, the higher the charge of metal, the larger the electrostatic interaction, the larger delta, right? So as I oxidize my metal, it's going to get smaller. I'm going to know the metal ligand interaction is going to increase, so therefore I'm going to see a bigger splitting occurring there for my octahedral. If I were to now go down a group, so if I were to look at different metals, so now if I look at group 9, and if I look at cobalt 3, rhodium 3, and iridium 3, and I were to measure delta octahedral for a series of amine complexes, so the ligands are the same, only thing I'm changing is the ligand, oxidation stays the same, only thing I'm changing is the ligand, is I'll see that as I go down the group, delta octahedral increases, right? So delta octahedral for cobalt 3 is going to be smaller than delta octahedral for iridium 3 complex, even if they have the same ligand. And one of the cool things now, what also affect the magnitude of delta is the nature of the ligand itself. So I'm showing you here all chromium 3 species, so chromium with cyano, NH3, water, and fluoride. And what we can see is that delta octahedral varies for each one of these different ligands. And what this is telling us is that the magnitude of delta octahedral is affected by the nature of the ligands. So in other words, different ligands is going to cause that splitting energy to increase, to be bigger or smaller, right? Depending on the nature of the ligand. So what we have is what we call a spectrochemical series, where we have a listing of ligands and we arrange them by how they influence delta octahedral. So if they cause a small split, we call these weak field ligands, right? And if they cause a large split, we call these strong field ligands. So examples of weak field ligands includes iodide, bromide, chloride, and thiocyanide and fluoride. Examples of strong field ligands is cyanide, carbon monoxide, ethylene diamine, and NH3. So the stronger the ligand binds to the metal center, the bigger delta octahedral is going to be. All right. I don't expect you guys to memorize the spectrochemical series, but I do expect you guys to get a sense of it, where halides are weak field ligands, water and oxalates tend to be weak field ligands, and then anything with a nitrogen or a carbon binding directly metal center tend to be strong field ligands, right? And those are going to cause a large split. Okay, so to iterate again, if I have, so here it is, I have chromium with 6 water molecules around it, a small split, right? If I have chromium with cyanide around it, it's going to cause a big split. And that's because water is a weak field ligand, whereas cyanide is a strong field ligand. And when they're bound to the metal center, they're going to change how big the splitting energy is. All right. Are we good? We're going to just end it there. No, it's not up yet. I will play up later. Okay, so let's end there. And then the next thing we'll talk about is filling the electrons and the consequences of being split. And then we'll jump into color, magnetism, and ligand stability next week for a final class. Yes, Justin.
So I remember my question. You know how in like
Mm-hmm.
the VSEPR originally we had to get a new theory to explain paramagnetism?
Mm-hmm.
Is this kind of like similar to it? Like,
Right. So you're right. So for crystal field theory, let me tell you right now, it's like a quick thing that if you are studying these complexes, you draw for. It, the reason why it works, it shouldn't work, but it works. And it works more time than none. So we use it for quick analysis of the d orbital splitting diagrams. Molecular orbital theory will be more precise, but it's the same thing. As we start to investigate the world around us and start to study things, whenever we find a result that does not fit into the paradigm, does not fit into the knowledge that we have at the time, we have to then upgrade our knowledge and come up with a new bonding model, new bonding theory to explain the phenomenon. Same thing, which is why I looked at molecular orbital theory when you're looking at O2, because according to VSEPR, then the O2 should not be paramagnetic, it should be diamagnetic.
okay,
Right?
thank you.
Okay. Yeah, man. All right. Any other question on this, or do we just want to, or are we good? Again, a lot of this, you guys just really have to just sit with it, read, and do some questions. Is a better way of getting this.
Stevenson, you said that
Yes.
we would have maybe gotten our results today. Is that still so, or
So I've heard from there's some students who've had problems with internet connections and they haven't been able to take the test. I thought about
Okay.
so I need to make sure that those people have been given the opportunity because it's not their fault that their data doesn't
Yeah.
work. They've been given the opportunity. Your tests have been graded. It's an RVLE, and I heard that some of you also want to be able to see the questions and see how you did on the questions. So I'm also going to have to clear with your different professor, different lecturers to see if they're okay with me showing you showing you their questions and the answers. But I was hoping to get them out today, but hang tight, maybe sometime tomorrow, I'll be able to release the grades.
Okay, thank you.
All right. All right, everybody. Have a good one.